All right, so welcome to module number 6. We're now going to start talking about models, and that will immediately lead to the minimum description length principle, which allows you to select a good model. It's related to what you may have heard in the past, Occam's razor, which is a principle that says that you should basically take the simplest explanation to the data that you have at hand, and we're going to formalize that. So first of all, models. We have three different concepts here. Models are mathematical abstractions for how we can interpret data. And data is in the real world, and it seldom, unless it's perhaps man-made data, but most data, a lot of data is not man-made. So in many cases, the data that is being modeled is more complicated than any of our models. And we also have algorithms that fit a model to the data. And of course, you can imagine that the main theme is going to be that complicated models, they perform well with the data, they give good performance, they model it well, but they're complicated to work with. And simple models are the opposite. They don't fit the data well, but they're simple to work with, and we need some common ground, some middle ground, a trade-off. So the question here is, are the algorithms good? How can we evaluate that? So the pros and cons of models are that, again, the model is a mathematical abstraction. Okay, it captures the essence of the data, the main part, and real-world data is typically more complex. And if the model is complex, it explains the data well, and this will likely be overfitting, but it's difficult to work with. Both mathematically, it's hard to analyze a complicated model, and algorithmically. A simple model, on the other hand, it's simple to work with algorithmically, mathematically, it's computationally tractable. However, it may not sufficiently capture the intricacies of the data. So we want some intuition about what is a correct, in quotation marks, model. So suppose that we have a large class of possible models to choose from. And so you have this large class of possible models, and you're going to have model 1, model 2, model 3, and so on. And we want to know what's the correct, in quotation marks, model. Why am I saying correct? Because, in quotation marks, because, as I said earlier, there's no correct model. There's no perfect model unless it's man-made data. Instead, there's a model whose complexity offers a reasonable trade-off with how well it explains the data. So if we have more data, then we can decide between more models, and we can perform more precise learning. Again, learning in quotation marks. We're trying to decide on a model that's reasonable and offers a good trade-off between complicated and simple models, and then we'll be using that model to explain the data. So we're going to be learning, meaning deciding what's a good model, and we may need a lot of computation to sift between lots of models. And especially if we have a large data set, sifting through lots of models with a large data set will be very difficult. So if we have more data, we can learn more, but it's hard, computationally hard. What about if we have less data, less computation, but less learning? So this leads to some fundamental problems. First of all, what's the optimal trade-off between data size, computation, and learning? So obviously, the more data that you have, the more that you can learn, but it may require somewhat more computation. And if you're willing to pour a ton of computation, then you can learn very well. And then there's the issue if you're constrained in terms of computation, even if you have a ton of data, it'll be hard to learn. And there are clear trade-offs here. Somewhat related to that, but not stressed in our course, what's the optimal way to perform some computation? Now, optimal is, again, sort of in quotation marks, because it would mean what's the way to perform some computation that minimizes resource consumption. And there could be a lot of resources: power consumption, chip area. These are kind of hardware types of metrics. Runtime, number of instructions performed. So on a computer, on a CPU, the number of instructions performed is probably a good metric. How much memory does your algorithm require? So there are a lot of metrics through which we can claim that something is optimal, but clearly we want to have, within this very complicated multidimensional space with lots of metrics, we want to know what the good directions are. That's clear. And there are some initial results in this space, but it's not that developed. So now that we know what we're trying to do, we want to choose a good model, and we understand that it's a trade-off. Let's talk about some details of choosing a correct model. Correct in quotation marks, meaning the best one within some class of models subject to some reasonable criteria. So we're going to begin with a model class capital C, okay? So capital C is going to be a not necessarily 5 models, but it could be a parametric class of models. So let's go from the simplest model class, would have a very finite number of models, 7 models, 23 models. So suppose, just to keep it simple, you have 23 models, and you're going to try to select the correct one. The C star for the best, the lowercase c star, the best model among this model class. And I should probably call this C1, C2, C3, but M1, M2, M3, that's fine too. So we're beginning with a finite model class. And we just have 3, or in this case, 23 completely different models. And now let's make it a bit more complicated. Suppose that you have one parameter, okay? You have one parameter, and we can discuss what that parameter could be. And that parameter might have a lot of values. In fact, the number of values could be proportional to the size of x. Could be maybe, if x has n entries, it could be square root of n or n cubed, or some relationship with the number of possible parameter values, each of them corresponding to a specific model. These are all going to be in the model class capital C. So let's make this a bit more concrete. So the parameter is going to be, or rather, my data will be binary bits, so zeros and ones, of length n. My parameter is going to be the percentage of ones. Now, how many ones could there be in the data? There could be 0, there could be a single one, 2 ones, 3 ones, up to n ones. So we have n plus 1 possible numbers of ones. And based on that, if you just count the number of ones divided by n, and then you specify that that's your estimated parameter, we have n plus 1 possible parameters. That's an example of a model class. So there's one parameter, and it takes on n plus 1 possible values. But now, suppose that we make this a bit more interesting. We still have one parameter, and that parameter is a percent from 0 to 1. Again, the parameter is the percentage of ones, the probability of ones, the empirical probability of ones in the data. And empirically, it's either 0 divided by n or 1 divided by n up to n divided by n. But you don't necessarily need n plus 1 of these. Imagine that you have 5, 7, whatever. So these are going to be bins in the range of probabilities from 0 to 1. And the arrows are going to be perhaps in the middle of the bins. And the arrows are going to be, think of it as quantization levels in a quantizer in signal processing. So inside each bin, you're going to look at the empirical probability, you're going to map it to one of the bins, and in each bin, there's going to be a representation level, perhaps at the middle of the bin. That that seems intuitive to us. And maybe the number of bins will be a function of n. And I can tell you already that we're going to see that if the number of bins is proportional to the square root of n, that's a good choice, okay? So now that is one parameter, but now suppose that you have more than one parameter. And suppose that capital C is a model class, and part of the model class is one parameter, and another part of the model class is two parameters. Now, to keep it simple, suppose that we have n models in this first part, okay? We have n models with a single parameter, and suppose that in the second subclass of models, we have, let's just say n squared. Doesn't need to be n squared, it could be n to the 1.7, doesn't matter, details, okay? But now think about it. The point that I'm conveying here is that a subclass that has more parameters is probably larger. So we can have, in our class of models, we could have, the simplest case is I have a finite number of models, 23, always 23, irrespective of the amount of the data. Somewhat more complicated case, I have one parameters, two parameters, a fixed number of parameters, and the number of models, the number of values for the parameters grows with n. It could grow in different ways. It could grow as I wrote here, n or n squared, and I told you that square root of n with one parameter has some good properties. So those details will be determined, but I'm saying that there could be a parametric class with a fixed number of parameters. So let's type that down. So the simplest model class C, we have a finite number of models. A intermediate model class, we have fixed number of parameters, and the number of models is basically increasing in n. The more complicated type of model class, and it can get more and more complicated, might be different subclasses, each different number of parameters. Could even be that you have infinitely many, okay? So I'm trying to provide the insight that model classes could be quite simple, 23, that's it. Or it could be that they get increasingly complicated. But within this model class, you want to choose the best one. All right, so let's continue. So given a specific lowercase c in our model class, x has a probability PC of x. And now our model class C, if it's complicated, if it's complex, it may have, in the example that's sketched in my Venn diagram, two parameters, and it may require a larger coding length to specify those two parameters. Now, why is that? Imagine describing the model within C as follows. The first bit is going to specify whether you're in the one parameter class or in the two parameter class. So let me change my color. Let's say that here in the one parameter class, my first bit is a 0. And in my two parameter class, my first bit is a 1. So I spend one bit describing which subclass I'm in. After that, if I'm in the first class with one parameter, to choose among n models, I need something like log base 2 of n bits. And the reason is, information theory tells us that if we have one bit, we can resolve between two possible model classes, two possible messages. If we have 2 bits, we can resolve between 4 possible messages, which is 2 squared. And to make this concrete, the combinations of the bits could be 0, 0, 0, 1, 1, 0, and 1, 1. So 4 pairs of bits. And if I have k bits, I can have 2 to the k possible messages. So here I have n models, and I need log base 2 of n within this subclass to specify which model I'm using. Now, what if the first bit, recall, the first bit decides between the model class of 1 parameter or 2 parameters. What if it was a 1? I have 2 parameters. Now I have n square models, and I need 2 log of n, 2 log base 2 of n bits to choose the correct model, the best model within that second subclass. So I'm saying that you need bits to describe the data, PC of x, and you need bits to describe the model, length of x. And the overall description, you need length of c to describe c, lowercase c, and length c of x, given that you've decided on c, to describe the data x. And you're looking for all the c's, all the specific individual models within capital C, our model class, and you're choosing the one that minimizes the sum length. That's the minimum description length principle. All right, so let's move to the next slide. So you can actually, this minimum description length approach, or MDL, we can convert it into bits as follows. Recall, C squared is the model C within the model class, capital C, that minimizes the sum of the 2 lengths, length of C to specify C, length C of x to specify x after we've specified C. And this results or suggests the following code. Part 1, specify C. The number of bits will be length of C, which is the negative log base 2 of basically every C is going to have a probability. Let's revisit our example from before. I'm going to have 2 model classes, 1 parameter and 2 parameters. And I've told you that typically for each parameter you want square root of n levels approximately, but forget about that. I'm saying that we have n possible values of the parameter in the single parameter case, and suppose that we have n square pairs of parameters for the 2 parameter case. So this is what I'm doing here is, as we will see soon, not so optimal, not the best. We can do better. However, let's just flow with this example. So we're going to need a bit to choose between 1 parameter and 2 parameters. And if we're in the 1 parameter case, we have another n possibilities. So let's differentiate between the 1 parameter and the 2 parameters. The total of all of these, because we needed 1 bit to specify between 1 or 2 parameters, we have a total probability of 1/2. And each of these n values for the parameter has probability 1 divided by 2n. Now, think about it. I have n possible parameters, n possible classes within the model class, capital C, so capital C for model class. N multiplied by 1 over 2n is 1/2, and 1/2 is the total probability assigned to this subclass. The second subclass with 2 parameters also has a total probability of 1/2, but it has n square parameters in it, and each of them has probability 1 divided by 2n squared. And when you take the n square models within the second subclass, n squared times that probability, 1 over 2n squared, gives us 1/2. 1/2 plus 1/2, probability 1/2 for the 1 parameter case, probability 1/2 for the 2 parameter case, sums up to 1. That's completely reasonable within our understanding of probability. So part 1, you specify C. Part 2, given C, you specify X. Now, the way how I've described it on the previous slide, if you have 2 bits, you can decide between 4 possible messages and so on. When you have an integer number of bits, when the log base 2 of a probability is an integer, that's simple. And I'm just saying that non-integer numbers of bits can be covered by a technique called arithmetic codes. And in the remainder of the course, I'd like you to just assume. And by the way, if some of you want to look at arithmetic codes for an individual project, I think that would be a great topic for an individual project at the end of the semester. But for the rest of the semester, you can assume that probabilities like a quarter are, of course, they correspond to 2 bits, and a probability like 1/8 corresponds to 3 bits, but probably like 0.17, you may assume that that can be handled also. All right, so let's continue. We have a formal approach for the minimum description length, and it's one possible approach. There are other approaches. It's related to an approach called maximum posteriori, or map estimation. In map estimation, we proceed as follows. We have the data. And I'm opening a text box here, which may not be visible to you guys. So we have the data, X, and for each model, we have a prior for that model, f of theta. And, or rather, for each model C, I use the notation C. I have PR of C. And now, given X, initially, there are different ways how I could proceed. I can calculate probability of X conditioned on C for each C. And one approach, which is called maximum likelihood estimation, says choose the C where the probability of X given C is largest. Okay? So maximum likelihood, choose argmax of probability of X given C. And by argmax, meaning that I choose the argument C that maximizes the probability of X conditioned on C. So that's one approach. But there's also this other approach. This other approach would tell you that every C has a probability. So that's approach 2. Every C has a probability. And we've ignored that in maximum likelihood. So now we want to maximize probability of C multiplied by the probability of X given C. Now recall, the joint probability is the probability of either C or X multiplied by the conditional probability of the other. So we're maximizing the joint probability of X comma C. And if PRC, if we have a prior means probabilities, if the priors for the C's are equal, are all the same, this is identical to maximum likelihood. But realistically speaking, oftentimes, as in my example with 1 parameter versus 2 parameters, that the models with 2 parameters, they have lower probability than the models with 1 parameter. So oftentimes the probabilities for the C's are going to be different. And then maximum a posteriori, which is what I just described, the second text box, gives more precise results than maximum likelihood. So MDL was formulated, again, related to maximum posteriori. It was formulated by various authors in the 1970s. This guy, Jorma Rissanen, was one of these authors. I must say that I learned recently, a few weeks ago, that he died earlier this year. And over the last 20 years, I met him in person 6-7 times, and I counted him as a friendly sort of guy. I liked him a great deal. So it was another major contributor to this scientific area is no longer with us. So his work, he did some of the pioneering work on the minimum description length, and it's closely related to Occam's razor. And below we have a picture of William of Occam, who lived many hundreds of years ago. And Wikipedia says that he stated that among competing hypotheses, the one with the fewest assumptions should be selected. So how do we perform model selection using MDL? Again, the MDL coding length for X minimizes the length given C of X plus the length of C, where we've seen that this has a correspondence to maximum posteriori, where the length of C is the probability for the model of C, and the length for X given C corresponds to the probability of X given C. And links are, recall, links relate to probabilities. The negative log of the probability. And because of that, adding links is analogous to multiplying probabilities. And we saw that multiplying probabilities in this case gives us the joint probability. So the joint probability PR of X jointly with C is the probability of C multiplied by the probability of X given C. And the links are length of X comma C is length of C plus length subscript C of X. Okay, so you can multiply probabilities, you can add links, same thing. And you're going to select the C that corresponds to the lowest total length, and statisticians often call this model selection. So maximum posteriori, or MDL, is one approach, but there's a fancier approach called mixtures. You assign a probability to X using all the models simultaneously. You assign a greater probability to the simpler models. So the length of X, or rather, let's, there's a typo here. The probability for X is a summation over the C's. For each C, we're taking the probability of that C multiplied by the probability of X given C. Now, let's think about what's going on here, and later I'll update the slide accordingly. So we have a Venn diagram, okay? And now we're saying, let's think of the Venn diagram as the model class, but area will now correspond to probability. So this is going to be C1. And this is going to be C2. And we're just going to look at C1 and C2. There are others also. Within C1, we have a lot of possible X's. This is the first possible set for X. We'll call it X1. This is the second possible X, X2. And maybe under C1, X3, maybe there are 3 possible X's. X3 has a large probability. And perhaps under C2, X3 has a small probability. And X2 has a small probability. And X1 all of a sudden has a large probability. So the ratio of the probability of X1 within the space for C2, that's the probability of X1 conditioned on C2. And the overall area that X1 takes within C2 is the joint probability. So this area is the probability of X1 appearing jointly with C2. And if X1 actually happened, the probability of X1 is the probability of X1 occurring jointly with C1 plus the probability of what I just jotted down, X1 appearing jointly with C2 plus the probability of X1 appearing jointly with C3 and so on. So if maximum a posteriori would have returned, if this is among the joint probabilities of some C with X, if that's the one with the largest probability, the largest area, or area in my schematic is proportional somehow to probability, if that's the largest, this is the area that MDL chooses. This is the probability that MAP chooses. But however, the mixture chooses the sum of that and this and other appearances of X1. And there are advantages and disadvantages with mixtures. It assigns a larger probability. By assigning a larger probability, not just the largest red, but the extra reds are added into. The larger area means larger probability, a smaller coding length. And this results in a more precise probabilistic model for X. However, mixtures are computationally challenging. In some cases, there are specific techniques that can computationally implement a mixture effectively, but oftentimes that's not the case. So another topic, if some people would be interested, would be if people want to learn about mixtures. So that'll be all for this module, module number 6, and we'll continue next time.